Here we have example 2, where we have another familiar function to graph. In this case, we're going to graph AC is equal to 135 plus 2q squared over q. Now this is the average cost function that we determined in concept video 4.03 earlier. And when we did that optimization, we determined a minimum average cost of 32.863 when Q was equal to 8.216. Now a quick overview of what we had done in that concept video 4.03. We had taken the first derivative of average cost, and I'm just going to jump to the conclusion. And what we determined was that the first derivative was 2q squared minus 135 over q squared. And this can be rewritten as 2 minus 135 q to the power of negative 2. We then solved for when this first derivative was equal to 0 to determine any maximum, minimums, or saddle points, really any stationary points, from which we determined q equals to 8.216 when this first derivative is equal to 0. And you can try that out. Plug in 8.216 into the formula and you'll see that this first derivative is equal to 0. Now to determine what kind of stationary point this is, we would take the second derivative AC double prime, and we would take the derivative of our first derivative here, and I'm going to use the version 2 minus 135 q to the power of negative 2, so that when I do this derivative, I get 270 q to the power of negative 3. When I determine what this second derivative is at our critical point of q is equal to 8.216, I sub that into our second derivative here, I get 0.487. Really, I'm just interested in the sign of our second derivative. It's positive, indicating that in the region of our critical point, it's concave up. The critical point is where that slope is 0, indicating that the average cost when q is equal to 8.216 is a minimum. Now, of course, I'm curious about what that average cost value is as well, so I'm determining what the average cost is when q is equal to 8.216. So I plug 8.216 back into our original equation because we want the average cost, not any of the derivatives. I get 135 plus 2 times 8.216 squared, all divided by 8.216. Then I get 32.863. That's where this value came from. So for this function, I can see that there's only one critical point, and it is a minimum. Now to examine other characteristics so that we can graph this function. Let's start with our intercepts. So when q is equal to 0, I'll get the AC intercept, or the vertical intercept. So I'm going to plug q is equal to 0 into my equation. And if you try plugging this into your calculator, you're going to get an error message because the reality is that you cannot divide by 0. This is an indeterminate function. So there's no answer. In other words, there is no vertical intercept. Now let's examine this to see if there's any horizontal intercepts. So when AC is equal to 0, then we get our horizontal intercept. So this is, just so you have a reference point, our average cost, and this is our Q value. In this case, we will expect Q to always be greater than 0, and average cost to always be greater than 0. So we're only looking at values in this region. So will AC ever be equal to 0? Will it ever cross that Q axis? Let's find out. So I'm going to set my AC to be 0, and I have 135 plus 2q squared all over q. So multiplying up by q, I get q times 0, so it doesn't really matter what that value is. Really, our denominator is never going to turn it to be equal to 0. It would be the numerator. So I'm going to move my q squared over here, and I get negative 2q squared is equal to 135. Dividing both sides by negative 2, I get q squared is equal to negative 67.5. And note here that we're squaring a value, so if we square something, it's always a positive, because a positive times a positive will give us a positive value, and a negative q value times a negative value, which is actually impossible as well, but theoretically it would still give us a positive. So no matter what, the answer on the left-hand side has to be positive, but we can see that this is a negative value. So this is not possible as well. Q squared can never be equal to negative 67.5. So again, this is not possible. So there are no horizontal intercepts as well. Okay, so this is getting a little bit trickier. We know that there's no vertical intercepts and there's no horizontal intercepts. So when we're looking at this function, we know that cost is really negative, and we can't produce negative amounts. And we know that we have a minimum when AC is equal to 8.216. So let's put that somewhere around here, 8.216. And that average cost was 32.86, and it's going to be a minimum. So 32 will be somewhere right around here. So this would be the minimum. And it's concave up at that point. That's how we know it's a minimum. That the slope is 0 there and it's concave up. We also know that this value the Q value can't ever be equal to 0. Remember that if the Q value is ever equal to 0, then we would have a denominator with a 0 value. So that is not possible. But it can get very, very, very small. It can skim close to 0. And what's going to happen as this gets close to 0, the smaller this value gets, the higher the AC gets. So it's going to form what we call an asymptote, where it goes and skims right up to that vertical axis, just like that. We can also look at what the nature of that second derivative is. Does that second derivative ever change? Is it going to be concave up forever? And so we can see our second derivative is 270 q to the power of negative 3. And because our q value is always positive, this value is always going to be positive, 270 is always positive, we know that our second derivative is always positive. So we know it's always going to be concave up throughout the entire function, no matter what the q value is. So what I'm going to do is I'm just going to kind of extend this out and look at other q values, such as 20. And I'm going to look at a q value such as 1. And I'm going to graph those 2 points and see what those values are so that I can get some framework for this image. So I'm going to take my original AC function. So AC is 135 plus 2q squared over q. And I know that AC, when q is equal to 1, is going to give me 135 plus 2 times 1 squared over 1, giving me 137. So now I can revise this image so that I know when q is equal to 1, I have 137, so that'll be 100, roughly 150. So 137 is probably right around here, and that's 1 right there. So I'm going to try to connect that. And AC, when q is equal to 20, I will have 135 plus 2 times 20 squared all over 20, giving me 46.75. So revising this portion right here, this will still be under 50, probably right around here. So a value right about there. So you can see that it is a lot more shallow right there. But this is my minimum right here at 8.216. So I got a rough idea of what the shape is. Now let's compare this to the graphs that we were given. And in an exam, this hand sketch that I did would certainly suffice. But let's look at the other sketches that we have. in our lecture handout as a reference, where we can see this shape of graph in the images for C and E over here. But looking at it a little bit closer, we can see that the scale on the horizontal axis for E is far more in line. Our minimum would have been right around here. And the values on the vertical axis are in line, where our minimum of 8 would have corresponded to roughly 32. So this would be the graph that we would be looking at, E.